Chemical equilibrium 6.3 Chateliers Principle. So at the end of this lesson, you should be able to state Chateliers Principle. And the second one is to apply Chateliers Principle to explain the effect of the following factors on a system at equilibrium. The first factor is the concentration of reacting species, and the second factor is pressure by changing volume. So what is Chateliers Principle? So it can be defined as when a chemical system is disturbed, it re-attains equilibrium by undergoing a net reaction that reduces the effect of the disturbance. Three common disturbances are: the first one is the change in concentration. The second one is the change in pressure, it caused by change in volume. And the third one is the change in temperature. Net reaction is shift in the equilibrium position of the system to either right or left. First factor, the effect of concentration of reacting species. When the reactants or products are added or removed from a chemical system, its concentration in the equilibrium mixture may be changed. So consider the following equation of reactants produced products. Okay, now we look at the first case, which is the reactant is added. So when the reactant is added, okay, you add reactant. So what will happen to the concentration? So the concentration of reactant will be increased because we add reactants. So the equilibrium will re-establish to decrease the amount of reactant because adding reactant is the disturbance. Thus, the equilibrium position will shift to the right. Okay, shift to the right. Okay, why? Because by shifting to the right, the reactant will produce more product. Thus, the concentration of the added reactant just now will be decreased. Therefore, the new equilibrium is achieved. Okay, now look at the second case when the reactant is removed. Okay, now you remove the reactant. The reactant is removed from the system. So, the concentration, okay, you remove the reactant. Okay, so the concentration of reactant will be decreased because you remove the reactants. So, the equilibrium will re-establish to increase the amount of reactant. Thus, the equilibrium position will shift to the left. Okay, because when it shifts to the left, the product will produce more reactant. Thus, the new equilibrium is achieved. Okay, now the third case is when the product is added. Okay, so when the product is added to the system, you add product. The concentration of product will be increased. The equilibrium will re-establish to decrease the amount of product because the addition of product just now is the disturbance. Okay, so how? So the equilibrium position will shift to the left. Okay, because by dissociate and produce more reactants, the concentration of product will be decreased. Okay, now the fourth case when the product is removed. Now you remove the product. Okay, we remove the product. So when the product is removed from the system, of course the concentration of product is decreased. So the equilibrium will re-establish to increase the amount of product. Thus, the equilibrium position will shift to the right, okay, to produce more product. Keep in mind, the equilibrium system only will disturb if the concentration of reactants or product in gaseous phase and aqueous phase are changed. So the change in concentration of solid or liquid substance has no effect on the equilibrium position. Why? Because the concentration of solid and liquid remains constant. Based on the following reaction, predict the direction of the equilibrium when the first one is adding NO. So what happens when you add NO? So the concentration of NO, of course, will be increased because we add NO. So the increase of NO is the disturbance in the system. So the equilibrium will re-establish to decrease the amount of NO. So we will be decrease back the amount of NO added. So how? So the equilibrium position will shift to the right. Okay. Now when we add NO2, so the NO2 is on the right hand side. You add NO2, so the concentration of NO2 will be increased. So the increase of NO2 is the disturbance in the system. So of course the equilibrium will react to decrease back the amount of NO2. So how? So the equilibrium position will shift to the left. Okay. So now when we remove N2O. So remove N2O. N2O also on the right hand side. Okay. You remove N2O means the concentration of N2O is decreased. So the decrease N2O is the disturbance in the system. So the system will react to increase back the concentration of N2O. So how to increase back the concentration of N2O? So the equilibrium position will shift to the right. And the last one, when we remove NO. So you remove the reactant on the left hand side. Okay, we remove the NO. So of course the concentration of NO will be decreased. So the decrease in NO is the disturbance. So the system will react, okay, will re-establish to increase back the concentration of NO. So how to increase back the concentration of NO? So of course the system will shift to the left, because when it shifts to the left, it will produce more NO. Based on the following reaction, predict and explain the direction of the equilibrium when the first one, add CO. So when CO is added to the system, CO is the product on the right hand side. So the concentration of CO will be increased because we add CO. Increase. So the increase of CO is the disturbance in the system. So the reaction, of course, will be re-established to decrease the amount of product CO, okay, to reduce the disturbance. Thus, the equilibrium position will shift to the left. Okay, it will shift to the left. Why? Because the system will consume CO. So when it consumes CO to produce reactant, of course the amount of CO will be decreased. Okay, now the second example is when we add carbon. So what will happen to the equilibrium position? So no change to equilibrium. Okay, why no change to equilibrium? Because the change in concentration of solid carbon. Okay, now look at the phase. Carbon is in solid phase. It will be no effect on the equilibrium position. Why? Because the concentration of solid C remain constant. Okay. Okay. Next, when we remove H2. Okay. We remove H2. H2 is the product on the right hand side. So we remove H2. So of course the concentration of H2 will be decreased. Okay. So the equilibrium will re-establish to increase. Okay, to increase the amount of product H2. Because just now you decrease H2. So the decrease of H2 is the disturbance in the system. So of course the system will react by increase back H2. So the equilibrium position will shift to the right because H2 decrease. So when it shift to the right, more H2 will be formed. So it will achieve the new equilibrium. Keep in mind, okay, when we increase concentration of reactants, okay, when we increase the concentration of reactant, so the shift in equilibrium will shift to the right. Okay, by reduce the increase in concentration of reactant, so it shift to the right. So when we decrease the concentration of reactant, okay, we decrease the concentration of reactant, so the system will shift to the left. Okay, so when we increase the concentration of product, now we increase the concentration of product. Product is on the right hand side, so of course it shift to the left. Okay, so if we decrease the concentration of product, okay, we decrease or we remove the concentration of product, so of course the system will shift to the right to produce more product. So exercise. So to improve air quality and obtain a useful product, sulfur is often removed from coal and natural gas by treating the fuel contaminant hydrogen sulfide with O2. So what happened to concentration if O2 is added? B. What happened to the concentration of H2S if O2 is added? C. What happened to the concentration of O2 if H2S is removed? And last one, D. What happened to the concentration of H2S if sulfur is added? So I hope you guys can answer all these questions in order to achieve learning outcomes of the subtopic.